Okay, welcome back. So now we're going to pick up with lecture 8.2, where we're going to discuss the relationship between CV and CP. Okay. So to do this, let's go back and start by remembering our CP. Okay. So CP experiments were done, by having a mass on our piston to keep the pressure constant, right? So we wanted a constant pressure on our piston. Okay? So we had CP was partial Q, partial T at constant P. Now, I want to invoke the first law to try to come up with a relationship between CV and CP. Okay, so the first law, remember, was du was dq plus dw. And for a reversible process, like a mechanical process that wasn't dissipative, we could have our work was minus P dV. Okay, so we're going to rewrite dq as du plus P dV. Okay, so we're going to write Cp. So think of Cp as dq dt, which we can rewrite as du, so this could be partial u, partial t at constant p, plus p dv dt constant p. Okay, so we know what partial u, partial t is, right? So that's just Cp, sorry. So let's just write it like this. Let's just write Cp was dq. So in this process where we're keeping the pressure constant, right, we can just say it's dq over dt. And so we're going to write dq. For this process, we know that we're only doing it for this kind of process, is du dt plus p dv dt. Okay, but here's the key. Du dt doesn't depend on process, right? Since u is a state function, this is an exact differential, so it's always the same. Okay, so this is Cv. And we can say that, so that's Cv plus P dV dt. Okay, let's look at what dV dt is. Well, we need our equation of state. Our equation of state is PV equals nRT, or V is nR over P. Okay, so dV dt is just nR over P. So that means that Cp is Cv plus P times nR over P. Or Cp is Cv plus n Or if I had written it in terms of the molar heat capacities, little Cp would be little Cv plus R. So these are excellent things to remember. Okay? So in fact, what's really cool now is you can actually imagine, well, so we already know this, that like, yes, right? So last time we did Cv for a diatomic gas and Cv for a monatomic gas, right? So we now have two ways to actually independently determine R. So we could do the experiment where we say measure Cp, and then we could also measure Cv for a gas, and we can determine the ideal gas constant, right? Or we could measure Cv for a diatomic gas, and we could subtract off Cv for a monatomic gas, and that also equals R. So we have two different ways. So go back and look at the values we gave last time, and you'll see that if you subtract Cv for a diatomic from a monatomic from a diatomic, you're going to basically get the ideal gas law, which is the ideal gas constant, which is 8.314 joules per mole. Okay. Very cool, right? That we can actually come up with this feature of an ideal gas through a real measurement, right? So now we have a measurement base for the ideal gas constant. So if you've ever wondered how you come up with a number like that, and actually now, we can relate this to Kb, right? We talked about how the ideal gas constant was related to Kb, right? So Kb was Nr over the number of mole, the number of atoms. So it'd be like, so if this were 1, right? So Kb would be 1 mole times R over Avogadro's number. Very cool, right? You can come up with something as fundamental as the relationship between a degree of freedom, right? If we know if we know Avogadro's number. Okay, very, very cool. So one thing that we're going to use to characterize gases, so how do I want to call it? Well, whatever. A way to characterize gases is through the ratio we're going to call gamma. So gamma is going to be Cp over Cv. So now you can see basically this is an intrinsic thing, so it doesn't even matter if it's big Cp, little Cp, per mass per as long as you're consistent. Okay, now we know that Cp is Cv plus R over Cv. So this is 1 plus R over Cv. And you can see that this number is always going to be greater than 1, right? Because it's 1 plus a number. So for a monatomic gas, gamma is going to be, so it's going to be our Cv for a monatomic was 3/2 R. So this will be 3/2 R plus R over 3/2 R. Right? Because there were 3 degrees of freedom for a monatomic gas. So this is 5/2 R over 3/2 R. So this is 5 over 3. And for a diatomic gas, right, gamma Well, we had that it was 5 degrees of freedom, so it was 5 halves r plus r over 5 halves r. So that is 7 halves r over 5 halves r. So that's 7/5. Very nice. Okay, so we're going to pause there with 8.2, and we're going to go on, and we're going to use these gammas now to explore a new process. Okay, and these are going to be called adiabats.